So Friday, we looked at the solubility rules. We started to look at some other kinds of chemical reactions. We looked at precipitation reactions. That is the ones that form solids when we put solutions together. We looked at gas forming reactions, the ones that we put two solutions together and a gas ends up bubbling up. We looked at acid-base reactions, where acid-base reactions where we have an acid and a base coming together, and usually we don't see a visible product, but we see other signs of a reaction in terms of pH change or a change in heat, or if we use indicators, a change in indicator color. Now we're going to focus mostly on precipitation reactions because for us, they're first of all, aside from acid base, they're probably the most common kind of reaction that we see in solutions. And the other thing about them is that from a visual standpoint, they're the easiest to kind of make note of. Looking ahead to your lab coming up after spring break. So I think this week you're doing types of reactions. So if some of the material from last week and balancing equations, recognizing those reaction types, if that kind of stuff was a little bit fuzzy last week, this week's lab should help to kind of reinforce some of that by actually getting to see those different reaction types in action. And then working to balance those equations as well. But for us, what we're looking at right now is we're continuing to kind of work ahead. And one of the labs that you'll get into in the weeks after break is a lab called the 9 bottles lab, where you're going to mix together a whole bunch of different combinations of solutions to see what happens and mark when reaction changes actually take place and when they don't take place. So what we're getting into today is we want to start as we're looking through the process here and trying to make some sense of it. What we want to start to do is we want to start to look at the overall concept of what a solution looks like. And so the chemical reaction that we are taking a look at here is this one, where we have potassium iodide reacting with lead-2 nitrate. Both of those are solutions. And we're told that the products of this reaction are lead-2 iodide, which is a solid, and potassium nitrate, which is aqueous, which means, again, dissolved in water. Now, we'll get to the product side of this reaction and how we can recognize that that product is going to be a solid versus not a solid. That all comes back to those solubility rules that we looked at on Friday. Let's move away from that for just a minute. Let's talk about the reactants themselves. When we have a solution, one of the parts that happens to make that solution is that the solid material has to be separated from itself. And that the water molecules get in there, break up that solid material, and start to surround each one of those molecules with water molecules. Now, in the case of an ionic compound, in addition to separating the molecules from each other, we actually see the separation of ions from each other. So it's not just enough to take that crystal of potassium iodide and split it up into individual potassium iodide molecules. What actually happens is because that potassium iodide is ionic, and because water also has positive and negative charges to it, what it does is it's going to split that potassium iodide into ions, into the potassium ion on one side and the iodide ion on the other. And the potassium ion and the iodide ion are each going to be surrounded by water molecules according to the charges on the water molecule. So the oxygen side of the water molecule is negative. It's going to line up around the potassium ions because potassium ions are positive. The hydrogen side of the water molecule is positive, so it stacks around the iodide ions because they are negative. Opposites ultimately attract. Well, this happens in every single example of an ionic compound. If I have an ionic compound, we're going to see separation not only of the molecules from the larger crystal, but from the ions to each other. And what we get in these solutions isn't an example of Ki, individual molecules in that solution, but rather K ions, K plus, and I ions, I negative, in that solution. And for the lead to or nitrate, it's the same thing. I'm going to have lead ions, and I'm going to have nitrate ions. The relationship between those come from the chemical formula itself. The chemical formula tells us that we have 2 nitrates for every 1 lead. And that would bear out in the solution itself. You can see that in this solution, I've got 1 lead and I've got 2 nitrates from that. Because the chemical formula tells us that that's the relationship. There are twice as many nitrates as there are leads. So when we start to look at these kinds of chemical reactions, that's one thing that we have to take into consideration. Individually, the solutions exist as ions in solution, not molecules in solution. And when we put them together, what we see is that the resulting solution is going to have all of those ions present in it at the same time. And this is ultimately why that double displacement reaction can take place. Why do we see partner switching in single replacement and double replacement? Well, because the ions themselves are not fixed to one element or another. The ions themselves are freely moving around in this solution. And so as a result, they are free to commingle, and in this case, move to a new partner. Especially if that new partner is going to offer them some kind of reactivity that wasn't there in their original solution. So ultimately in this set, what we'll see is that the potassium, the lead 2 ion, the Pb plus 2, is going to attract those iodine ions to it, because in that reaction, the lead 2 plus and the iodine minus are going to be able to form an ionic compound that is strong enough in its bonding that the water can't pull it apart the way that it could pull apart the individual solutions they had initially. And so that's what we start to see. The lead and the iodides start to interact with each other. They start to react with each other. The resulting compound, lead 2 iodide, is not able to be dissolved. It is more strongly bound to itself than what water can do by pulling it apart. And so we talk about a precipitation. Lead 2 iodide we would describe as the precipitate, the thing that is ultimately falling out of this solution and forming a solid in the bottom of this test tube or beaker or whatever it is that we do this reaction with. Now, because reactions in solution have so much more complexity to them, we need another way of writing them out. So take, for example, the reaction that we just looked at, where we had the lead nitrate and the potassium iodide. Both of these were in solution, reacting to make potassium nitrate and led to iodide. This is what we call a molecular equation. Molecular equations give us very specific information about the chemical reaction, but it does lack in some details. So, for example, we know that we started with lead-2 nitrate solution. We know that because we can see lead-2 nitrate as a reactant and aqueous as the phase, which tells us that it's dissolved in water. That's a solution. We also know that we had potassium iodide as a solution because we have potassium iodide as a reactant, and it's written as in the aqueous phase, which means it's dissolved in water. And we know that the reaction yielded potassium nitrate in solution and lead-2 iodide as a solid. The problem with this reaction type is that while it does give us a lot of information, that information is somewhat incomplete and also somewhat inaccurate. As we just saw in the 3-panel illustration there, lead-2 nitrate doesn't exist as lead-2 nitrate, the molecule. It exists as lead ions and nitrate ions in that solution. The potassium iodide does not exist as potassium iodide compound. It exists as potassium ions and iodide ions in that solution. And so in situations like these, where it becomes a lot more important to know the details and to know the exact nature of the reactants and the products, a molecular equation will not do. We need something a little bit more specific, a little bit more detailed. And this is where a ionic equation can come into play. What an ionic equation does is it shows us the exact environment of our molecular equation. How do these molecules actually exist in their reacting medium? And that's what sets this kind of equation apart. Now, in order to make an ionic equation or a complete ionic equation, what we need to do is we need to take advantage of a couple of things. One of them is we need to have a balanced chemical equation, which usually we're given, or if we're not given it, we can find our way to it relatively quickly. The other thing that we need is we need some knowledge. In particular, we need knowledge of the solubility rules to determine whether we are going to have an aqueous solution where everything is split up, or if we're going to have a compound where everything is still together. That's the challenge, and that's where we bring in this other stuff that we saw at the end of last week. So for the purposes of this exercise, we're going to look at this equation right here. Silver nitrate reacting with sodium chloride to make silver chloride and sodium nitrate. Now, this is what the ionic equation for that particular reaction looks like. Key features, things that we should point out, things that we should recognize. If we identify one of these reactants as being aqueous, notice that when we identify it as aqueous, we're seeing it split apart if it's ionic compound. So the silver nitrate was split up into the silver ion and the nitrate ion. Sodium chloride was split up into the sodium ion and the chloride ion. Sodium nitrate in the products was split up into the sodium ion and the nitrate ion. Silver chloride wasn't split up at all. And the reason it wasn't split up at all is because we need to recognize its phase of matter was marked as solid, which means it's not dissolved in the water. And if it's not dissolved in the water, it's not going to break apart into ions. And so for any phase that is not aqueous, that's exactly what we're going to do to it. So if I have a liquid, if I have a solid, if I have a gas, those phases don't break apart in an ionic equation because they're not actually dissolved in the water. The only things that break apart are the things that are dissolved in water, and that's assuming that they're a strong electrolyte. Which, again, since we're focusing on precipitation reactions, that's most of the time. When you get into acid-base reactions or some of the gas-forming reactions, it's not a necessary conclusion that if it dissolves in water, it necessarily breaks apart, because some weak acids and weak bases don't split apart because they don't make strong electrolytes. But we're keeping things relatively simple and straightforward here. So since we're only focusing on precipitation, we can make that assumption. If it's aqueous and ionic, it breaks. And we start to look for, okay, what are the ions that it is making? If it's not aqueous, keep it together, because that's how it's going to stay in that equation. As we go through more examples of these kinds of breakdowns, what we'll start to notice is that one of the byproducts of splitting up our molecular equation into ions is that we should start to recognize that some ions don't actually participate in the reaction. So if I take a look at this ionic equation for the reaction that we've been working on, the silver and the nitrate reacting with the sodium and the chloride, what I should start to see is that the nitrate ion is the same as a reactant as it is a product. The sodium ion is the same as a reactant as it is a product. This kind of circumstance is not unique. In fact, it's really quite common. When we do precipitation reactions, when we do most reactions in solution, chances are going to be pretty good that regardless of what it is that we are reacting, not every component of it will react. And those things that do not react, those that stick around but don't actually do anything, we call those spectator ions. A spectator ion is a component of a solution that doesn't participate in a chemical reaction. It's there, we know it's there, but it doesn't actually do anything. It just kind of sits around and watches. And that's why it's called a spectator. Now, our most common spectator ions are those ions that we see. We go back to the solubility rules. Remember that first slide of solubility rules that I gave you, the ones that are always soluble? Those are also your most common spectator ions. So we're talking about your nitrates, your acetates, your ammonium ions, your group 1 cations, so all of the alkali metal ions, all of those are your very common spectators. And so you can see that even here. Sodium's a group 1. So it's always going to be a spectator. Nitrate always dissolves in water. So it's going to always be a spectator. Because spectator ions can kind of junk up the overall picture, we can see there's a lot of redundancy here. I've got sodium on both sides. I've got nitrate on both sides. Maybe a little bit difficult to see the forest for the trees here. And that's why we have something called a net ionic equation. What the net ionic equation does is it pulls out all of those spectator ions and allows us to just focus on the things that change. So in the example problem that we've been working off of, the things that change are the silver ion and the chloride ion. They started as unattached ions initially, and now by the end of it, they are in a solid together. So we've seen a drastic change in their properties. We've seen a drastic change in their makeup. It isn't just silver ion anymore. It's now part of this compound silver chloride. And again, the big thing to kind of point out and kind of work our way to here is just in the recognition of our solubility rules. If I didn't do this reaction in the lab, if I didn't know from the molecular equation that it was a solid, how would I predict that this was going to happen? I'd go to my solubility rules. The solubility rules tell me that chlorides are usually soluble, except with mercury, lead, or silver. Silver being one of those exceptions. I know to expect silver to react with chloride and give me a solid. So this is where that stuff that we talked about on Friday starts to kind of overlap with this new stuff. Because ultimately the solubility rules are a predictor. They help us to predict when things are going to happen and when things aren't going to happen. Because we can look at things like net ionic equations and see, oh, in this particular case, everything was aqueous on both sides. And if I take it all the way down to the ionic equation, I'll see that they're all spectator ions and that nothing actually changed. But if I use the solubility rules and I say, oh, wait, we started with solutions over here, I've got this solid over here, there's my evidence of a chemical reaction. Now I have a net ionic equation that tells me exactly what did happen, and everything else is just kind of background noise. So just to kind of put all of this into perspective before we get into actually drawing out some equations. Again, a molecular equation gives us all of the details, but from 30,000 feet. Tells us what reacted, tells us what the solutions or what the reactants look like, tell us what the products look like, but they don't give us a whole lot of detail, and they certainly don't tell us how we get from point A to point B. They just tell us what happened overall. The ionic equations give us that more detailed, boots on the ground kind of viewpoint. Tell us these are the ions present in this solution, these are the ions present in this solution, these are the things that are present at the end. And then a net ionic just helps us to scrub out some of the extra noise by focusing only on the things that change. So high level, minimal detail, extreme detail for complete ionic, essential detail for net ionic. That's the difference between the three. Now let's put all this into action. So for calcium chloride reacting with magnesium sulfate, first of all, we're told that both of these are aqueous. We could verify that using our solubility rules. So, for example, chlorine, chlorides are usually soluble, except for mercury, lead, or silver. Calcium's not one of those. So we would be able to correctly determine that this is a soluble compound here based off of those rules. Same thing for the sulfates. Sulfates are usually soluble except for the Balcomer sulfates. Magnesium is not one of those, so it dissolves as well. Now, this is an example of a double replacement or double displacement reaction. How do we go about recognizing those? Well, what we're looking for are two ionic compounds as my reactants. So if I have two ionic compounds, then I know that I'm dealing with double replacement. If I have one ionic compound and an element, that's single replacement. The difference is how many compounds am I looking at on each side. In double replacement, the cations, which are usually the metals, are going to switch places. So I'm going to have magnesium and chloride, and I'm going to have calcium and sulfate. Now, before I finish those off, I want to make sure that I've got the formulas correct. For that, I need to know the charges that we had initially. So calcium I can get directly off the periodic table. It's +2. In these reactions, the charges don't change. So it started as calcium +2. It's going to end as calcium +2. For chloride, I can look at the periodic table. Chloride is in group 17. All of the group 17s have a -1 charge. So this is going to be a -1 charge over here as well. For magnesium, magnesium is also in group 2. It's also an alkaline earth metal. It's always +2. Sulfate, if you didn't know, if you forgot that one off of the polyatomic ion list, by virtue of the formula, you'd be able to guess its proper charge. How would you be able to guess it? Well, if you recognize sulfate as SO4, There's no additional subscript on it, right? Which means that its charge has to match the other charge. And if I know that magnesium is +2, that means I have to know that sulfate's -2 as well, because the charges have to match, or else we'd have other subscripts. We don't. So sulfate has to be -2 as well. So now we gotta look at the compounds themselves. Are the compounds being shown with the correct formula? So we've got the ions properly switched. Do we have the formulas right? Answer to that, in this case, is no. My charges do not match. Since the charges don't match, I've got a crisscross. So 2 goes down here, 1 goes down here. It's going to be MgCl2. For calcium sulfate, the charges in this case do match, +2 and -2. So the formula is correct as it is. From a balancing standpoint, I can see that I have calcium, chlorine, magnesium, and sulfate on both sides. I got 1 calcium over here, 1 calcium over here, 2 chlorines here, 2 chlorines here, 1 magnesium, 1 magnesium, 1 sulfate, 1 sulfate. All of the categories match. All the categories are even. So this is a balanced chemical equation now. We don't have to do anything further with it. So we've satisfied the first part. We've got a molecular equation. Now let's get into the next part, the more difficult part. I've got to figure out if these dissolve or not, and then I've got to break them apart into ionic and net ionic equations. So for the first part here, let's get this stuff out of the way. Okay, magnesium chloride. Now we got to go to our solubility rules. Magnesium doesn't have a set rule, but chloride does. Chlorides are usually soluble, except for with mercury, lead, or silver. Magnesium is not any of those. So since it's not an exception, it is the rule. We already determined that these were soluble. This is soluble as well. So we can put an AQ next to the magnesium chloride, since we know it's going to dissolve in water. For sulfates, so again, no set rule for calcium, but we do have a set rule for sulfates. Sulfates are usually soluble except for the Balcommer sulfates. Barium, lead, calcium, mercury. Well, calcium is one of those exceptions. So it's the exception, not the rule. The rule was soluble. The exception would be insoluble. So this one's going to be solid. turn our equation into an ionic equation, I need to separate out the things that are soluble, split them into their ions. So that means I'm going to have calcium ion, and I'm going to have chloride ions. Now, this is a really important piece right here. Remember that when we are making ionic compound formulas, subscripts are there for charge balancing purposes. So chloride ion isn't Cl2 negative. Chloride ion is Cl negative. We know based off of the periodic table what kind of ion chloride makes. Cl with a -1 charge. Where's this 2 come in? Well, again, it's there for balancing purposes. I need 2 of these chlorides to balance out the charge of the calcium. So when you see subscripts like these, the important thing to remember is that you want to pull them out, because that's what they really are. They're there for balance purposes, to tell you that you have multiple ions of that kind. And that tells you in the equation sense that we have multiple ions of that kind. We pulled it out and made it a coefficient. For magnesium, it was magnesium +2 and sulfate -2. We didn't have to do anything with those. On the product side, we had the magnesium ion, Mg +2, and we've got the chloride ion, Cl -1. And again, the 2 here gets pulled out to show that balance of charge. 2 chloride ions to balance out the 1 magnesium. Calcium sulfate, we leave alone. Since it is insoluble and it did not dissolve in the water's not going to pull it apart into its ions. It's going to stay together. So those ones are easier, at least by extension. So this is the ionic equation for that reaction. How do I turn it into a net ionic equation? Well, I need to look for spectators. I need to look for things that are common on both sides. And honestly, the way to do this is to work backwards. Look at ions in the product side of the reaction and see if there are matching ions on the other side of the reaction as well. So I've got a magnesium ion here. Is there a magnesium ion as a reactant? The answer here is yes. So that's a spectator ion. That one we would pull out. Similarly, fluoride ions. I've got 2 on this side. Do I have 2 over here as a reactant? Yes, I do. So there are no more ions on the product side of the ledger here. So I know I can't go any further. That's why you always want to work backwards in this kind of situation instead of trying to do matchups. Because if it's not in the product side, it's not going to be it doesn't matter if it's going to be on the reactant side or not. To turn this into a net, all I need to do is just rewrite the stuff that is not a spectator, the stuff that does not cancel out. So it's the calcium ion and the sulfate ion making calcium sulfate. In essence, that is the chemical reaction that took place. Those calcium ions reacted with those sulfate ions to make calcium sulfate. And visually, you would see that as a white solid, because that's what calcium sulfate looks like. It's white. All right, any questions with this material before we call it a day? Yes. So that's a really good question. Question was, do you have to show phases? And the answer there is, it depends on who's asking. In mastering, sometimes they get very picky about that and they want you to show all of the phases. So if they ask for it, yeah, any of the ions would be aqueous, and then the compound would be solid. I tend not to be as picky about those things just because it's one more thing to remember how to do. And obviously, if you're showing an ion, it's going to be dissolved in water. So I take more of a common sense approach to it. But yes, mastering can be a little bit finicky about that. So just something to watch out for. I'm going to give you an opportunity here just to get a participation point. So go ahead and do the stoplight here. We're not done with this lesson. I'm going to extend it. This is going to be the first thing that we do coming off of break as well. So this assignment being due Thursday, don't worry about that. We'll push it off. But it is open. So if you want to just kind of see how you're doing and how you feel about this particular concept, go ahead and do so. But we'll come back to this after break as well. Have a good day.